Welcome back to Fun Facts Online. Today, we are not talking about incremental improvements. We are talking about a fundamental wall in physics and how humanity is trying to break through it. For the last 20 years, if you follow technology, you followed one metric, the nanometer. We went from 90 nanometers to 45 to 14 and down to the 3 nanometer chips that are currently sitting in your pocket or running the massive AI data centers of the world. That number, the node, was our North Star. It promised that every 2 years things got faster, smaller, and more efficient. But as we look toward 2026, that era is effectively dead. We have hit the hard limits of what silicon and traditional geometry can do. The components of a modern transistor are now measured in handfuls of atoms. The nanometer is simply too blunt a tool to describe where we are going. We are entering the Angstrom era. Specifically, we are racing toward the 2 nanometers node, or 20 angstroms, and beyond that to 18A and 14A. To understand why this is such a big deal, you have to realize that this isn't just about making things smaller anymore. The 2 nanometers chip represents a complete reinvention of how a computer chip is built. We are discarding the transistor architecture we've used for 15 years. We are flipping the power delivery system upside down. We are using light so extreme it gets absorbed by almost everything in the universe. And we are switching materials because copper, the king of conductivity, has finally met its match. So let's break down the engineering marvels that are keeping Moore's law on life support. First, we need to look at the architecture. For the past decade, since about 2011, every high-performance chip has used something called a FinFET. Before 2011, transistors were flat, like drawings on a piece of paper. But as they got small, they became leaky. Electrons would slip across the channel, even when the switch was off, wasting power. The FinFET solved this by pulling the channel up into a 3D vertical fin. It looked like a shark fin rising out of the silicon. This allowed the gate, which is the on-off switch, to wrap around the fin on 3 sides, left, right, and top. That 3-sided control clamped down on leakage and let us scale down to 3 nanometers. But at 3 nanometers, the FinFET has run out of gas. To get more performance, you need taller fins, but they are becoming so tall and narrow that they are structurally unstable. They can literally collapse. Furthermore, you can't fit enough fins in the footprint to drive the current we need for modern computing. So the industry is moving to the Gate-All-Around FET. Depending on who you ask, it's called a RibbonFET, a nanosheet, or an MBC-FET. But the concept is the same. Imagine taking that vertical fin and turning it sideways, so it becomes a stack of horizontal sheets floating in the air above the silicon, like a stack of paper suspended by the edges. Now, the gate material can wrap completely around each sheet, top, bottom, left, and right. This provides the ultimate electrostatic control. Leakage is virtually eliminated because the channel is surrounded on all 4 sides. But there is another massive advantage here: tunability. In the old FinFET days, if you wanted more power, you had to add another fin. You could have 1 fin, or 2 fins, or 3. You couldn't have 1.5 fins. It was discrete. With nanosheets, engineers can vary the width of the sheets continuously. If you need a high-performance core, you make the sheets wider to drive more current. If you need a high-efficiency core, you make them narrow to save power. This allows chip designers to mix and match transistors with incredible precision. But building this is a manufacturing nightmare. It's like building a suspension bridge at the atomic scale. They start by growing alternating layers of silicon and silicon germanium on the wafer. Then, they have to etch pockets into those layers to build inner spacers. And then comes the magic step, the channel release. They use a chemical etch to selectively remove the silicon germanium layers completely, leaving the silicon sheets floating with gaps between them that are less than 10 nanometers wide. Then, they have to use atomic layer deposition to fill those tiny gaps with the gate material, 1 atomic layer at a time, ensuring there are no air voids. It is arguably the most complex manufacturing step in human history. Now, while the transistor is getting a total makeover, we are also seeing a revolution in how chips are wired. This is the second pillar of the Angstrom era, backside power delivery. For 60 years, chips have been built like a pizza. The dough is the transistors at the bottom, and the toppings are the layers of wiring stacked on top. In modern chips, you might have 15 to 20 layers of metal wiring. The power and the data signals fight for space in this same complex web. The power has to travel from the very top of the stack down through all those layers of increasingly thin wires to reach the transistors at the bottom. This causes 2 huge problems. First, resistance. As wires get thinner, they resist electricity more. By the time the power reaches the transistor, a significant amount of voltage has been lost as heat. This is called IR drop. Second, signal interference. High power lines create noise that messes with the delicate data signal sitting right next to them. The solution is to separate them completely. We are moving the power to the basement. With backside power delivery, Intel calls it Power Via, TSMC calls it Super Power Rail. The data wires stay on the front of the wafer, but the power wires are moved to the back. Here is how they build it. They make the transistors and the signal wires on the front, just like normal. Then they take the entire silicon wafer and flip it over. They grind the back of the silicon substrate down until it is vanishingly thin, just microns thick. Then, they drill nano holes, called nano-through-silicon vias, directly into the back of the wafer to connect power lines straight to the source and drain of the transistors. This eliminates the long, resistant path from the top. The power gets a superhighway straight to the transistor, virtually eliminating IR drop. It also frees up about 20 to 30% of the space on the front side, meaning we can pack the logic cells tighter together. But this introduces a terrifying risk: heat. The silicon substrate used to act as a heat sink. When you grind it away to add power lines, you are trapping heat right next to the transistors. Engineers are currently inventing exotic cooling solutions just to keep these chips from melting themselves. Let's move on to the third pillar, the machine that makes it all possible. To print features this small, we are transitioning to high-NA EUV lithography. Current EUV machines use extreme ultraviolet light with a 13.5 nanometer wavelength. But at 2 nanometers, even that isn't precise enough. We need high numerical aperture systems. These machines, made by ASML, are the size of a double-decker bus and cost nearly $400 million each. They use massive mirrors to capture light at wider angles, sharpening the image. But there is a quantum mechanical problem here called stochastics. At these scales, light stops behaving like a continuous wave and starts behaving like a rain of particles, photons. When you are trying to print a tiny wire, you might only be hitting it with a few photons. It is like trying to paint a fine line with a spray can. If you don't spray enough dots, the line looks jagged, or you get gaps. This is called photon shot noise. A single gap in a single wire can kill a chip worth thousands of dollars. The industry is having to use massive AI analytics to predict where these random quantum defects will happen and adjust the design to compensate. Finally, we have to talk about materials. Silicon is the hero of the semiconductor world, but copper has always been the hero of wiring. That relationship is ending. In wide wires, copper is great, but as wires shrink below 20 nanometers, we hit a physics problem. The mean free path of an electron, the distance it travels before hitting an atom, becomes larger than the wire itself. The electrons start bouncing off the walls of the wire, like a rubber ball in a hallway. This causes resistance to skyrocket. On top of that, copper needs a barrier layer to stop it from leaking into the silicon. That barrier takes up space, but conducts no electricity. The solution? Ruthenium. Ruthenium is a metal that is chemically stable, meaning it doesn't need a thick barrier layer. And while it is less conductive than copper in bulk, at the Angstrom scale, it wins, because you can make the wire solid metal. Intel is even pioneering a subtractive process, where they etch the ruthenium away to form wires, allowing them to leave air gaps between the wires. Air is the perfect insulator, which speeds up signal transmission. So who is winning this race? There are 3 main players. Intel is betting the entire company on a strategy called 5 nodes in 4 years. Their 18A node is coming in late 2024 or early 2025, and they are trying to integrate both the RibbonFET and backside power simultaneously. It is a massive gamble. If they pull it off, they could have a significant efficiency lead. TSMC, the current king, is being more conservative. Their M2 node in 2025 will introduce nanosheets, but they are waiting until 2026 to add backside power. They prioritize yield and trust over being the first to break things. Samsung is the aggressive challenger. They were actually the first to launch Gate-All-Around transistors at 3 nanometers, but they have struggled with yield. Their 2 nanometers node is their chance to prove that their early start gave them the experience to win. But regardless of who wins the transistor race, the way we package chips is changing too. The era of the single massive system on chip is dying. You simply cannot manufacture a massive 2 nanometers AI processor without defects. Instead, we are entering the era of chiplets. We are breaking processors into smaller, specialized pieces and stitching them together using advanced packaging like CoWoS and hybrid bonding. Hybrid bonding is fascinating. It fuses the copper pads of 2 chips directly together, allowing for connections that are 1,000 times denser than standard solder bumps. This allows us to stack memory directly on top of CPUs or logic on top of logic. The transition to the Angstrom era is an inflection point. The costs are staggering. Fabs now cost $25 billion. The physics are brutal. We are no longer just shrinking drawings. We are engineering with quantum mechanics. But the reward is the continuation of the digital revolution. As we look even further ahead to FETs, where we stack transistors on top of each other, and 2D materials like tungsten disulfide, one thing is clear. The engineers of the Angstrom era are refusing to let Moore's law die. They are rewriting the rules of reality, one atom at a time. Thanks for listening to this deep dive on G Fun Facts Online.